Imagine, just for a second, that you get a splinter.
Oh, yeah, the absolute worst.
Right. Like you're doing some yard work or whatever, and you brush your hand against a rough piece of wood.
And you just immediately feel that tiny sting.
Exactly. A tiny, almost invisible fragment of pine just buries itself into the skin of your thumb. And you don't really think about it.
No, you usually just ignore it.
But your body doesn't. Your body absolutely freaks out. Almost immediately, this incredibly sophisticated biological alarm bell goes off.
The immune system wakes up.
Yeah, it floods the area. The thumb gets red, it swells up, it gets hot to the touch. Your body recognizes that this tiny piece of wood, it does not belong there.
It's an invader.
Right. And it begins this relentless microscopic war to push that foreign object out.
I mean, it is a remarkable defense mechanism. It's really the reason we, as a species, survive even the most basic environmental encounters.
But now I want you to imagine that instead of a piece of wood in your thumb, you are putting a piece of metal or silicon or synthetic plastic deep inside your brain.
Which is a horrifying thought, honestly.
It really is. But for the last 20 years, some of those brilliant scientists on Earth have been trying to figure out how to, politely ask the human brain to just ignore the splinter.
So let the metal stay?
Yeah. And for you, listening right now, if you're looking for that massive perspective-shifting aha moment about where human technology is actually heading, you're in exactly the right place.
You really are.
Because today, our mission for this deep dive is to explore a radically different approach. We are looking at a startling, almost manifesto-style research paper.
It's called The Organic Quantum Interface by Zachary David Enfield.
Right, and it lays out a completely new blueprint for a brain-computer interface, or a BCI.
It's a fascinating document, because Enfield is drawing a hard line in the sand here.
And he really is going after the whole industry.
Yeah, he's making the argument that every single thing we think we know about connecting a computer to the human brain is built on a fundamentally flawed premise.
Like we're just barking up the wrong tree.
Exactly. We've been trying to solve the wrong problem entirely.
Right, because everything the public currently knows about BCIs is based on this idea that we just need to build a better, softer splinter.
A less intrusive one, yeah.
We think of the Utah array, which literally looks like a tiny, stiff bed of nails pressed into the brain.
Very medieval.
Super medieval.
Huh.
Or we think of Neuralink's approach, which is like a microscopic sewing machine threading incredibly thin, flexible polymer wires into the tissue.
Making the wires smaller and softer. That's the whole obsession.
Yeah, the whole industry is obsessed with that. But Enfield says no. He claims the future of brain interfaces isn't going to be a microchip at all.
Not even close.
He suggests it's going to involve radioactive isotopes, engineered yeast prions, and organic quantum physics.
Which sounds completely insane on the surface.
It sounds like sci-fi. Okay, let's unpack this. Where do we even begin with how current BCIs are getting it so completely wrong?
Well, we have to start by taking a really close look at that biological alarm bell you mentioned. The paper refers to it as the biology of rejection.
Or the crisis of the electrode paradigm, right?
Yes, because every single brain-computer interface built to date relies on what we call a synthetic transduction layer.
Okay, synthetic transduction layer.
Yeah, it's just a highly technical way of saying the part of the machine that physically touches the brain is made of something synthetic.
Like silicon or plastic.
Exactly. Silicon, tungsten, or engineered polymers. And the underlying engineering assumption has always been that if we just make these foreign materials structurally mimic the brain will eventually just tolerate them.
So they treat it as a pure materials problem. Like, if I can just make this plastic feel exactly like brain tissue, the brain will be fooled.
That is the driving philosophy of the field right now. They look at the mechanical differences between a computer chip and a brain, which, are undeniably vast.
Right.
For instance, rigid silicon has a modulus, which is an engineering measure of stiffness of about 200 gigapascals.
Okay, 200 gigapascals. How does that compare to the brain?
To put that in perspective, brain tissue is incredibly soft.
Yeah.
It's essentially the consistency of a very delicate jello.
Wow, okay.
It sits at around 15 kilopascals.
So gigapascals down to kilopascals. That is a massive structural mismatch.
It's massive. If your brain moves inside your skull and you have a stiff silicon spike sitting in it, that spike acts like a tiny knife.
Oh, just slicing the delicate tissue. That's awful.
It is. So the engineers naturally say, well, let's make the spike out of jello, too.
Right, or as close to it as they can get.
Yeah, they try to bridge that mechanical gap. You see research teams using polyethylene glycol dimethylacrylate.
Let me guess, that's a type of hydrogel.
Exactly, it's a hydrogel.
Yeah.
They use it to coat the rigid silicon and soften the blow. Or they move away from metals entirely and use conducting polymers.
Like P-GOD PSS, right?
Yes, which can carry an electrical signal, but are much softer. Or they use flexible parylene C substrates that are designed to literally bend, float, and sway with the natural pulsations of your cerebrospinal fluid.
Instead of scraping against the walls of the tissue, which just on a purely technological level sounds like absolute magic.
It really does.
They're building microscopic, electrically conductive seaweed that floats inside your head. It's phenomenal engineering.
Oh, it is stunning engineering. The problem, according to Enfield, is that it is solving the entirely wrong problem.
Why?
Because there's a phenomenon that plagues the whole BCI industry. It's called progressive signal degradation.
Meaning the signal just gets worse over time.
Yes. When you implant a BCI, it might work beautifully on day 1 or even day 30. But slowly, over months or years, the signal gets weaker and weaker until eventually the device is completely deaf.
And I'm guessing the industry views this as a failure of their material.
Exactly. But Enfield points out that it isn't a failure at all. It is a massive success of the brain's immune system.
Because the brain is doing exactly what it evolved to do. It's finding the splinter.
Yes. The brain doesn't just evaluate objects based on how soft they are. When you insert a synthetic probe, no matter how flexible it is, the brain's resident immune cells immediately investigate it.
The reactive microglia and astrocytes.
You got it. And they don't just feel it, they essentially taste it. They detect a surface chemistry that simply does not belong in a biological system.
Because it doesn't match the native tissue.
Right. It lacks the complex, aromatic, hydrophilic, protein-coded language of your actual brain.
It's like trying to use a completely fake ID at the most heavily guarded bouncer in the world.
That's a great analogy.
Like, the ID might be printed on really soft, flexible plastic, but the bouncer can still read the barcode and see it's totally fake.
That's exactly it. And once the microglia realize it's a foreign object, they mount a specialized immune response. It's called glial scarring.
Glial scarring, what does that actually look like?
They swarm the electrode, they encapsulate it, they literally build a biological wall around it to separate it from the healthy brain tissue. But they don't just stop at walling it off. In the process of trying to break down the foreign invader, these immune cells generate reactive oxygen species.
Okay, what does that actually mean in practice? Reactive oxygen species.
It means they are unleashing a localized chemical attack. This creates severe oxidative stress right at the site of the implant.
Oh, so it's attacking the device itself.
Exactly. And this stress literally corrodes the active electrode surfaces. It eats away at the microscopic conductive materials and degrades the insulating layers.
So it's a vicious cycle.
A self-amplifying cascade, yeah. The more the electrode corrodes, the more the immune system attacks it, building a thicker wall.
Which pushes the electrode further away from the neurons it's trying to listen to.
Exactly. You lose the signal entirely.
It makes total sense when you lay it out like that. It means that wrapping a metal electrode in a really soft hydrogel is basically like wrapping a splinter in velvet.
That's exactly what it is. Like, it might be softer, it might not cause as much immediate friction or tissue tearing, but your body is still smarter than that. It knows it's a splinter, and it wants it out.
And it will win that fight eventually.
Which leaves us staring at a pretty massive wall. I mean, if the brain naturally, inevitably rejects all foreign objects, how do we ever achieve a permanent, high-fidelity connection to it?
That question is the core pivot of Enfield's entire proposal. The paper argues that we have to fundamentally abandon the quest to build better electrodes.
Stop trying to trick the bouncer.
Exactly. Instead, we need to start building a conversation partner that the brain naturally recognizes as itself.
An organic interface.
Yes. We need an interface that isn't engineered from synthetic polymers coated in stealth materials, but a biological scaffold built from the exact same fundamental molecular components that the neurons themselves use to communicate.
Which means, before we can even begin to build that biological interface, we have to understand the secret native language the brain is actually speaking.
We do. And this brings us to section 2 of our deep dive. This is a huge paradigm-shifting revelation about the neuron itself. And honestly, this part absolutely blew my mind when I read it.
Oh, it's incredible.
Because it turns out the classical model of neuroscience, the exact model that you and I and everyone listening learned in high school biology is incomplete.
It is vastly incomplete.
Let's get into it.
So the classical model, the one that forms the basis of all current BCI engineering, focuses almost exclusively on action potentials.
Those are the electrochemical waves that propagate down an axon, right?
Right. It's the story of sodium and potassium ions moving across a cell membrane and neurotransmitters being released across a synaptic cleft to trigger the next neuron.
The brain as a giant wet electrical switchboard.
Exactly. And that model is entirely accurate for describing the macro-scale behavior of neural networks. It's how large regions of the brain talk to each other.
But Enfield is zooming in further.
Much further. Enfield's paper synthesizes decades of emerging biophysics to show that when you zoom in deep inside the individual neuron, down past the membrane, down to the scale of individual proteins, the neuron is not just a biological wire.
What is it?
At its most fundamental level, it operates as a quantum optical device.
Okay, we need to slow down and really ground this. Because for anyone listening, hearing quantum optical device inside the human brain sounds like pure science fiction.
I know, it sounds crazy.
It sounds like something out of a cyberpunk novel. Let's break down the actual physical hardware here.
Yeah.
What is the physical structure inside the cell that is doing this?
The central structure of interest here is something called the microtubule.
Microtubules. I remember those from cell biology.
Yeah, they are part of the cytoskeleton. They are cylindrical lattice polymers, meaning they look like incredibly tiny hollow tubes.
And they're made of protein.
Made of a protein called tubulin, yes. And when I say tiny, I mean they are roughly 25 nanometers in diameter.
They're small.
For decades, biologists thought these were just structural scaffolding, basically just the microscopic bones of the cell that maintain the shape of the long, spindly axon.
But I aren't just the bones.
Far from it. They're also the densest concentration of aromatic amino acid chromophores in the entire cell.
Okay, aromatic amino acid chromophores. Let's unpack that, because when most people hear aromatic, they think of something that smells good, like coffee or perfume.
Right, right.
But in chemistry, it means something very different, right?
Yes. In organic chemistry, an aromatic ring is a specific molecular structure. It's a ring of atoms, usually carbon, where the electrons aren't tied down to one specific bond.
That sort of float around.
Exactly. They're delocalized. They form a sort of electron cloud that floats above and below the ring, and this gives them very unique electromagnetic and quantum properties.
So how many of these rings are we talking about inside a microtubule?
It's a staggering number, and it's organized with mathematically beautiful precision. The fundamental building block of the microtubule is the tubulin dimer. And inside every single one of those dimers, there are exactly 86 aromatic rings.
86.
Specifically, there are 8 tryptophan, 36 tyrosine, and 42 phenylalanine residues.
Okay, so we have this hollow tube made of proteins, and embedded inside those proteins are thousands of these ring structures with floating electron clouds.
And the arrangement of those rings is what changes everything. Enfield highlights that those 8 tryptophan residues aren't just floating around randomly in the protein soup.
They have a pattern.
Yes, they're spatially arrayed in a highly specific geometry. The center-to-center spacing between these tryptophan rings is exactly 1 to 2 nanometers.
And why is that specific measurement 1 to 2 nanometers so crucial to this whole theory?
Because it's not a random number. That precise angstrom-level geometry perfectly mirrors another biological structure that we already understand very well.
Which is?
The Fenner-Matthews-Olson, or FMO, photosynthetic complex.
The one found in plants?
Found in certain green plants and bacteria, yes.
Okay, photosynthesis. This is a massive leap, but I know it's central to the paper. Let's take a slight detour. Explain what the FMO complex is doing in a plant and why it matters to the human brain.
Sure. When a plant leaf absorbs sunlight, it captures a single photon of light.
Right.
That photon's energy needs to be transported from the surface of the leaf deep into the reaction center of the cell where it can be turned into chemical food.
But the inside of a biological cell is incredibly messy.
Very messy. If that energy just bounced around like a pinball, it would lose all its momentum as heat before it ever reached the destination.
But it doesn't. Plants are incredibly efficient.
Almost 100% efficient, actually, which classical physics couldn't explain.
So how do they do it?
It wasn't until the mid-2000s that physicists realized how plants do it. The proteins in the plant leaf use quantum superposition.
Quantum superposition inside a plant.
Yes. The energy doesn't take one single path through the messy cell. It exists in a quantum state, exploring all possible paths simultaneously, and instantly collapses into the single most efficient route. And the biological hardware that allows the plant to hold that quantum state is a specific arrangement of aromatic rings.
So Enfield is saying, if we look at the brain's microtubules, we see the exact same architectural blueprint that plants use to do quantum physics.
Yes. The spacing, the orientation, and the dipolar properties of the tryptophan chromophores in the human brain's tubulin are structurally and mathematically predicted to do the exact same thing as the plant leaf.
They form quantum coherent conduction pathways.
Exactly. They aren't conducting classical electricity, they are conducting quantum states.
So if I'm trying to visualize this,
Yeah.
reading a classical action potential with a traditional metal BCI like the Utah array is essentially like reading the printed receipt at a grocery store.
That's a good way to look at it.
It tells you the final total.
Yeah.
But this quantum optical layer inside the microtubule, that's the actual cash register. That's the complex high-speed machine doing all the intricate math before the receipt even gets printed.
I think that captures the essence of it beautifully. The action potential, the electrical spark that neuroscientists have been measuring for a century, is just the macro-scale residue.
The exhaust fume.
Yes, the exhaust fume of a cognitive process that has already been completed at a level of speed and resolution that a classical electrical spike simply cannot encode.
What kind of speeds are we talking about?
We are talking about terahertz frequencies.
Yeah.
Trillions of operations per second at the quantum optical level, which then determine the microsecond timing of the nerve cell's electrical firing.
But wait, I have to jump in and push back here. Because if you read anything about quantum computing, the first thing you learn is that quantum states are incredibly fragile.
Extremely fragile, yeah.
Like Google and IBM build these massive multi-million-dollar quantum computers, and they have to keep the processors inside these giant cryogenic chandeliers cooled down to absolute zero in a complete vacuum.
Right, to prevent decoherence.
Exactly. Because if there is even a tiny bit of heat or vibration, the quantum state collapses.
Wow.
So physicists have argued for decades that the human brain is simply too warm, too wet, and too chaotic to sustain quantum physics.
Right. You're touching on what was, for a long time, the most formidable argument against quantum biology. It's called the decoherence problem.
So how does the paper resolve that? How does the brain not destroy its own quantum computer with its own body heat?
By turning the problem into the solution, it goes back to that photosynthesis research. It turns out biological systems didn't just find a way to survive in all that thermal noise. They evolved to actively exploit it.
Exploit the noise.
Yes, it is a mechanism known as phonon-assisted quantum transport.
Break that down for us. What is a phonon in this context?
A phonon is a quantum of sound, or in this case, a discrete packet of vibrational mechanical energy. It's the mathematical description of that thermal jiggling from body heat.
Okay, so a phonon is just a bit of heat vibration.
Right. Now, in a standard man-made quantum computer, yes, that jiggling destroys the data. But inside the specific, tightly woven protein structure of the microtubule, the thermal vibrations, the phonons, actually couple to the electronic states.
As they work together.
Exactly.
Yeah.
The scaffolding is tuned so precisely that the background noise acts like a steady drumbeat. It sustains and actually enhances the quantum coherence, pushing the excitons along the pathway.
That is mind-blowing.
The heat of the brain doesn't destroy the quantum state. It is the very engine that drives it.
That completely flips the script. And if you're listening to this on your commute right now and thinking, wait, my brain is generating terahertz quantum frequencies using body heat, I mean, it is a mass lot to take in.
It's a total paradigm shift.
It really is. Yeah. But if you are trying to understand where the future of computing is going, realizing that the human brain operates on nested frequencies, that it uses terahertz optical vortices at the quantum level, which then dictate the gigahertz, megahertz, and kilohertz cascades all the way down to the classical hertz range of an electrical pulse.
Yeah.
It fundamentally changes your entire understanding of what human intelligence actually is.
It forces us to stop seeing the brain as a complex telegraph machine. We have to start seeing it as a multi-layered quantum classical hybrid system.
They aren't separate.
No, the classical electrical networks and the quantum protein layers are not two separate things. They are nested scales of the exact same coherent architecture.
So if we accept this premise,
Yeah.
if we want to eavesdrop on this terahertz speed quantum computer, if we want to ditch the printed receipt and wiretap the actual cash register, we need to know exactly where to place our microphone.
Exactly. We know we need to listen to the microtubules, but the brain is a big place.
Which brings us to section 3, the target. Why does Enfield's blueprint specifically aim for the prefrontal cortex?
Well, to understand the target, we have to understand what we are trying to extract. The prefrontal cortex, or the PFC, located right behind your forehead, is the anatomical seat of executive function.
It's where the complex thoughts happen.
Yes, it is where everything that makes you, you essentially happens. It's the home of working memory, complex decision-making, abstract reasoning, and impulse regulation.
Can you break down the specific regions within the PFC that the paper highlights?
Certainly, the paper specifically isolates the dorsolateral prefrontal cortex.
And what does that do?
That handles high-level cognitive control, like holding a phone number in your head or doing math.
Okay, what else?
And the ventromedial prefrontal cortex, which integrates those cognitive thoughts with emotional and affective processing to make value-based decisions.
But this is a huge departure from what current BCIs do. I mean, if you look at the viral videos of people using Neuralink or older BCIs, they usually target the primary motor cortex.
Yes, they do.
They are reading the brain to let a paralyzed patient move a mouse cursor or control a robotic arm. Why abandon the motor cortex?
Because the motor cortex is just an execution hub. If you are decoding signals from the motor cortex, you are decoding a physical command that has already been formatted, packaged, and sent out for execution.
To use your earlier analogy, you are reading the letter that has already been written, sealed, and dropped in the mailbox.
Precisely. It's incredibly useful for restoring movement, but it's fundamentally limited.
Because it doesn't give you access to the thought behind the movement.
Exactly. Or, to take that a step further, it doesn't give you access to the thoughts that never become movements.
Right.
If we can successfully target the prefrontal cortex, we can read the author's intent as the decision is actively crystallizing in their working memory. We can interface with abstract concepts before they are ever translated into a physical action or a spoken word.
That is the ultimate dream of a brain-computer interface.
Yeah.
Pure, unadulterated thought to text or thought to machine.
It really is.
But here is the massive logistical roadblock that comes to mind. The prefrontal cortex is deep, complex, folded tissue.
It is.
And we've just spent 20 minutes establishing that we cannot use metal or plastic because the immune system will attack it.
Right.
So if we can't build a massive, stiff probe, how on earth do we reach these deep cognitive thoughts without drilling deep into the brain tissue itself?
What's fascinating here is that evolutionary anatomy has already solved that structural problem for us.
We don't have to drill.
We don't have to drill down at all. The prefrontal cortex has a highly specialized structural feature. The primary cell types doing the heavy lifting in this region are called layer V and layer 3 pyramidal neurons.
Okay, layer V and layer 3.
Their cell bodies are located deep within the cortical tissue, but they have the most elaborately ramified apical dendritic trees in the entire human brain.
Let's translate that for the listener. What is an apical dendritic tree?
Think of a neuron like a tree. The cell body is the roots, buried deep in the soil. The axon is the taproot going further down. But reaching upwards toward the sky are the dendrites.
The branches that receive incoming signals.
Right. In these specific layer V and layer 3 neurons, these apical dendrites act like giant vertical antennas. They stretch upwards from the cell body, spanning 2 to 3 millimeters, and they terminate in a massive, dense canopy of branches right at layer 1.
And layer 1 is significant because, why?
Because layer I is the pile surface. It is the absolute outermost superficial skin of the brain. It sits right beneath the skull and the protective meninges.
Oh, wow. So the deepest, most complex thoughts occurring down the cortex are physically reaching up to the very surface of the brain.
Yes. And crucially, those dendritic tips at the surface are not just passive biological wires carrying electrical current. They are incredibly dynamic.
What are they doing up there?
They are packed dense with the active quantum optical microtubule networks we discussed in Section 2. They are generating their own localized calcium sparks and participating in the massive nonlinear integration of information that underlies our working memory.
So we don't need a microscopic bed of nails. We don't need to plunge a needle into the delicate tissue at all.
Not at all.
We can access the brain's deepest, most complex computational layers just by gently touching the outermost surface of the brain.
Exactly. We bypass the tissue damage entirely by reading the signals at the canopy rather than digging to the roots.
Okay, this brings all the pieces together into Section 4. We know exactly where to connect the pile surface, and we know we have to speak the quantum optical language of the microtubules.
Right.
But we still have that very first problem we talked about, the bouncer.
The immune system.
Yeah. What material do we actually use to make the physical connection? If metal triggers the immune system and plastic triggers the immune system, What on earth is left?
Enfield's proposed material is a biologically synthesized scaffold.
Made from what?
It's made from an amyloid fibril. Specifically, he proposes engineering a sequence derived from a protein called SUP35, which is a translation termination factor natively found in yeast.
Okay, wait, hold on a second. Stop right there.
I know where you're going.
When you say the words amyloid or prion, anyone who's ever read a medical article instantly thinks of horrific, untreatable neurodegenerative diseases.
Absolutely.
We're talking about Alzheimer's disease, amyloid plaques, mad cow disease. You're telling me this visionary paper proposes taking a prion, the exact thing that destroys brains, and laying it directly onto the surface of a healthy human brain.
I completely understand the visceral reaction to those words. It sounds highly alarming.
It sounds reckless.
But we have to separate the structural class of the protein from the pathology. Not all amyloids are disease-causing.
Really?
Really. Amyloid simply refers to a specific way that proteins fold together. And the structural stability of an amyloid fibril, specifically its cross-beta sheet spine, makes it one of the most robust, resilient biological assemblies known to science.
So it's tough. How tough are we talking?
It has a Young's modulus, that stiffness metric we discussed earlier, of 3 to 20 gigapascals.
Okay, wow.
That means this biological protein is comparable in strength and stiffness to engineered nylon or spider silk. It is incredibly tough, capable of surviving the mechanical environment of the brain without degrading.
Okay, I can accept that it's physically tough.
Yeah.
But why use a yeast prion? Why not use a human protein if you're trying to hide from a human immune system?
That is the absolute genius of the design, and it perfectly counters the immune system problem. The SUP35 is a yeast protein. It is completely absent from the mammalian proteome.
Meaning humans don't naturally have it anywhere in our bodies.
Right. And because we don't naturally have it, the human immune system has no evolved evolutionary program to attack it.
Wait, really? If it's foreign, wouldn't it attack it immediately?
Not necessarily. If we used a human protein, the body might recognize it as misfolded and trigger a massive clearance response to clean it up. But because it's from yeast, it doesn't match any pathogenic threat profiles, and it doesn't trigger the autoimmune cascade pathways.
So it just slips under the radar.
Exactly. It is structurally non-toxic and biologically acceptable. To the brain's immune system, to the bouncer, it effectively just looks like inert background biology. It sits there, functionally invisible to the immune response.
So it's tough enough to act as a physical device, and the immune system totally ignores it, but it's still just a piece of yeast protein.
Right.
How does a simple, natural protein conduct the highly advanced quantum information we talked about?
That is where the natural biology meets incredibly precise molecular engineering. Enfield doesn't just want to drop a natural yeast prion onto the brain.
He modifies it.
He outlines a process to take the minimal amyloid-forming segment of that yeast prion, which is a specific 8-amino acid sequence, an octopeptide called CGNNQQNY, and chemically modify it.
Modify it how?
By forcibly inserting a tryptophan residue at exactly every fourth position in the sequence.
Tryptophan.
Yeah.
Wait, that's the aromatic ring with the floating electron cloud. The one that does the quantum processing in the brain's microtubules.
Yes, and the placement is absolutely critical. Because of the predictable, rigid way that the beta strands of a prion fold and stack on top of each other, if you place a tryptophan exactly every fourth residue, they end up spaced perfectly 4.8 angstroms apart along the entire vertical length of the fibril.
Let me give the listener a visual anchor here.
Yeah.
Imagine a spiral staircase inside a lighthouse.
Okay, I like this.
If you painted a bright red stripe on exactly every fourth stair, and then you stood at the very top of the lighthouse and looked straight down the center, you wouldn't see a spiral of red paint.
Right.
Because of how the stairs overlap, all those red stripes would perfectly align into one single straight red column going all the way down to the floor. That is what they're doing with the tryptophans, right?
That is a phenomenal visual. Yes, by engineering the sequence that way, they force those aromatic rings to stack perfectly parallel to each other. They create continuous, unbroken columns of pi-stacked aromatic rings.
Here's where it gets really interesting. By doing this, we aren't just making a medical implant. We are essentially 3D printing a nanoscale organic quantum wire from scratch.
And we are doing it at the exact right scale. The resulting engineered fibril has a diameter of 5 to 10 nanometers.
Which is tiny.
Which, not coincidentally, perfectly matches the scale and the aromatic density of the brain's own native microtubules inside the dendrites.
Okay, so let's summarize the board state as we enter Section 5. We have built a synthetic quantum wire out of heavily modified yeast proteins. We
Yes.
have bypassed the immune system. We've laid this invisible wire directly on top of the brain's natural quantum wires at the very surface of the cortex, aiming right at the prefrontal thought centers.
Okay.
But there is a glaring physical issue here. They aren't actually touching.
No, they are not. There is a physiological barrier called the glia limitans and the protective membranes of the cells themselves. There is a microscopic empty gap between our engineered yeast scaffold and the actual working brain tissue.
So if they aren't touching, and there are no classic electrical wires connecting them, how does the terahertz quantum data actually cross the gap?
The signal jumps the gap via a phenomenon called first-order resonance energy transfer. In the field, it is universally referred to as FRET.
Okay, unpack FRET for us, because when I think of energy jumping a gap, I picture a spark plug in a car engine or a spark of static electricity jumping from my finger to a doorknob. Is it like that?
No, not at all. A spark is a physical transfer of mass. It's actual electrons tearing through the air to reach the other side.
Oh, okay. So what is FRET?
FRET is an entirely non-contact, radiationless process. There are absolutely no physical electrons crossing the empty space. It is a pure quantum optical phenomenon based on dipole coupling.
We need another analogy here to ground dipole coupling.
The best way to visualize FRET is to think of two acoustic tuning forks.
Okay.
Imagine you have a tuning fork calibrated to a very specific note, say middle C. You strike it and it begins to vibrate.
Right.
If you bring a second tuning fork, also perfectly calibrated to middle C, very close to the first one, something magical happens. Even though they never physically touch, the second tuning fork will begin to vibrate and sing with the exact same energy as the first.
Just through the air.
Yes, the energy transfers through resonance.
But with tuning forks, the distance between them is super critical for that resonance to take hold, right?
Incredibly critical, and the math governing FRET is brutally unforgiving. The efficiency of FRET energy transfer decays as the inverse sixth power of the distance between the two molecules.
Inverse sixth power. So it's not a gradual fade out. It's an absolute cliff.
It's a sheer drop. If you double the distance between the two tuning forks, the energy transfer doesn't drop by half. It drops by a factor of 64. It is an effect that only exists at the extreme nanoscale. But this is where the anatomical genius of the paper shines. The physical gap between our engineered amyloid scaffold resting on the glia limitans and the terminal tryptophan residues inside the brain's dendrites sitting just below the surface is exactly 2 to 5 nanometers.
It's a perfect sweet spot.
Exactly. At that specific 2 to 5 nanometer distance, the FR3 energy transfer efficiency is calculated to be between 50 and 80%. The proximity allows the dipole fields to overlap perfectly.
So the data just naturally synchronizes and hums across the gap. The artificial yeast wire starts vibrating with the exact same quantum thought state as the biological brain.
Seamlessly.
And the paper notes that this resonance creates a bidirectional interface. It's a two-way street.
Yes, and that is absolutely vital for an advanced BCI. The scaffold can read neural quantum states by accepting excitonic excitations, which are the bound states of an electron and an electron hole, transferring from the brain's microtubules into the scaffold.
So that's the reading part.
Right. But just as importantly, it can write directly into the brain's working memory by reversing the FR3 process. It can transfer engineered excitonic excitations from the scaffold across the gap back into the brain's dendritic tree.
Okay, so we have successfully built a bidirectional quantum optical organic machine that is continuously reading and writing our deepest cognitive thoughts at terahertz speeds without triggering the immune system.
It sounds like magic, but it's physics.
But any machine that does work needs power. Which brings us to section 6. Obviously, you can't just slap a lithium-ion battery on the surface of the brain.
Definitely not.
They are way too large, they eventually die and need replacing, and the chemicals inside them are incredibly toxic. How do we power this matrix?
We don't use batteries at all. The scaffold is designed to be entirely self-powered indefinitely. It utilizes what Enfield calls a trimodal ambient energy harvesting system.
Trimodal, so 3 different ways of getting power.
Yes. Rather than bringing a power source into the brain, the implant literally draws continuous power from 3 independent energy sources that are already naturally occurring in the neural environment.
Let's go through these 3 distinct power sources, because each one is wilder than the last. Let's start with the one that sounds the most dangerously insane.
Beta-voltaic harvesting.
Beta-voltaic harvesting. The paper proposes incorporating actual radioactive isotopes into the brain implant.
Yes, directly woven into the protein backbone of the yeast scaffold itself. The proposal specifies using mildly radioactive isotopes like tritium,
Tritium.
which is an isotope of hydrogen with a 12.3-year half-life, or carbon-14, which has a massive 5,730-year half-life.
Okay, I have to stop you. We absolutely have to clarify the safety here. Because putting radiation in the brain immediately makes me think I'm either going to get a massive tumor or turn into a comic book mutant.
It's a completely natural reaction.
Why doesn't a radioactive brain implant cause severe radiation poisoning and melt your prefrontal cortex?
It comes down to the specific type of radiation. These isotopes undergo what is called beta decay. As they decay, they emit beta particles, which are essentially high-energy electrons.
Okay.
The kinetic energy of those electrons is captured by the scaffold and converted into tiny electrical currents. Now, the reason it doesn't harm you is because of the incredibly short physical range of these specific beta particles.
How short is short?
The maximum energy of a tritium beta particle is about 18.6 kilo-electron volts. In a dense biological tissue, which is mostly water, a particle with that energy travels a maximum distance of less than 6 micrometers before all of its kinetic energy is entirely deposited and absorbed.
6 micrometers is virtually nothing.
It is microscopic. It means that the entire lifespan of the radiation event begins and ends entirely within the physical dimensions of the scaffold itself.
Wow.
All the emitted energy is captured locally for electrical conversion. The radiation literally never reaches the surrounding healthy brain tissue. It is completely biologically contained.
That's a brilliant application of physics. Okay, so that's the nuclear battery.
Yeah.
What is the second ambient power source?
Piezoelectric harvesting. This is the capturing of physical mechanical energy. You might not feel it, but your brain is constantly in physical motion.
Wait, really?
Yes.
Yeah.
Every single time your heart beats, the sheer force of that cardiac pulse transmits up through your cerebrovascular tree, and it physically vibrates the cortical surface of your brain at a rhythm of about 1 to 2 hertz.
And breathing too, right?
Yes. The rhythmic expansion of your lungs creates pressure oscillations in the chest that translate up to the skull, vibrating the brain at a slower 0.2 to 0.4 hertz.
So the brain is just physically jiggling all day long inside the skull. How does the device turn a jiggle into electricity?
Through the piezoelectric effect, certain materials naturally generate an electrical charge when they are physically stressed or deformed.
Like pushing on a lighter, right?
Exactly like that. The native beta sheet structure of our amyloid protein scaffold is inherently piezoelectric. When it gets stretched, squished, or compressed by the brain's heartbeat-driven jiggling, the molecular deformation generates an electrical polarization.
That's so clever.
Enfield also proposes enhancing this natural effect by embedding microscopic barium titanate nanoparticles into the scaffold to maximize the mechanical to electrical conversion rate.
Okay, so we have nuclear decay, we have the mechanical heartbeat. What is the third and final power source?
Thermoelectric harvesting, which harnesses something called the Seebeck effect.
The Seebeck effect.
Yes. It dictates that if you have two ends of a conductive material at different temperatures, the heat differential will drive electrons from the hot side to the cold side, creating a continuous electrical current.
And the brain is hot.
The brain is incredibly hot. It is the most metabolically active organ in the body, generating about 1.5 watts of heat per 100 grams of tissue.
That's a lot of heat.
So the surface of the brain, deep under the skull, sits at a very warm 36 to 37 degrees Celsius. However, your scalp, which is exposed to the ambient air of the room you're sitting in, is cooler, typically around 30 to 35 degrees.
So there is a permanent temperature gradient.
Exactly. There is a persistent 2 to 7 degree thermal gradient between the hot brain and the cool outer skull. The scaffold acts as a thermocouple, generating continuous trickle power just by existing between those two temperature zones.
It's like an ultra-advanced automatic watch. But instead of just relying on the physical swing of your arm as you walk to wind the mainspring, this biological watch is powered by local nuclear decay, the hydraulic pounding of your heartbeat, and the literal metabolic heat of your deep thoughts.
That's a really poetic way to phrase it, but it's entirely scientifically accurate.
That is wild.
And importantly, the brilliance of the trimodal system is redundancy. None of these three methods has to provide all the power alone.
They work together.
The output is the aggregate of all three systems working in tandem. The tiny currents are pooled and buffered by a nanoscale capacitor integrated into the device, providing enough continuous, reliable energy to run the signal transduction, the data encoding, and the wireless transmission for the entire lifetime of the human host.
All right, so we've got our organic quantum wire, we've got our target, and now the whole system is fully powered up. This brings us to Section 7. Let's assemble all these wild components into the final architectural blueprint.
The six-layer stack.
Yeah, the paper outlines a six-layer stack. Walk us through how this entire symphony operates, starting from the brain and working upwards.
The foundation, layer 1, is the quantum coupling layer. This is exactly what we discussed with the FRT mechanism.
Sitting right on the pile surface.
Yes, it is the engineered amyloid aromatic yeast scaffold sitting right there. Its sole job is to establish that non-contact tuning fork resonance with the brain's dendrites, capturing the pure analog quantum state of the microtubules.
But having a vibrating tuning fork doesn't do us any good if we can't record the note it's playing. We need a way to enhance and sense that quantum data, which leads to layer 2.
Yes, layer 2 is the biomineralization enhancement layer. In this layer, they embed nanodiamonds into the scaffold.
Nanodiamonds?
But these aren't just jewelry diamonds. They have specific atomic defects called nitrogen vacancy, or NV centers.
What does a defect in a nanodiamond actually do?
An NV center acts as an ultrasensitive quantum optical sensor. It is capable of reading the minute magnetic fields generated by the quantum spin states in the amyloid layer below it.
Oh, so it reads the data.
Furthermore, highly metabolically active brain tissue naturally emits ultra-weak packets of light called biophotons.
The brain glows.
Very, very faintly. Yes, these diamond NV centers capture those stray biological photons and convert them into even more supplementary electrical power while simultaneously using them to read the state of the magnetic field.
Okay, so we're reading the quantum data beautifully. But if this device is only reading terahertz quantum poetry at the protein level, aren't we going to miss the classical macro-scale electrical spikes that the brain still uses to actually do things like move our muscles?
That is exactly the problem layer 3 solves. Layer 3 is the piezoelectric signal conditioning layer. We mentioned earlier that the piezoelectric properties harvest power from the heartbeat.
Right.
But it also acts as a mechanical sensor for the brain's electrical activity.
Wait, a mechanical sensor for an electrical signal, how does that work?
It's a fascinating physical reality of biology. When a classical electrical action potential fires down a neuron, it doesn't just send electricity.
What else does it send?
The change in voltage causes water molecules to rush into the cell membrane, which produces a literal, physical, nanoscale mechanical shock wave, a tiny physical bulge that travels down the nerve.
So the nerve actually bulges.
Yes. This piezoelectric layer physically feels that microscopic shock wave. It provides a classical electrical signal channel to perfectly complement the highly abstract quantum data.
So basically we have this beautiful, incredibly dense, but very messy biological data coming from the bottom 3 layers. But a standard computer, or a smartphone, can't read an analog quantum magnetic field or a mechanical shock wave. We need a translator.
Which brings us to layer 4. Layer 4 is the power and signal IC.
IC meaning integrated circuit.
Yes. This is a nanoscale integrated circuit chip physically bonded to the top of the biological scaffold. It acts as the brain of the implant.
And what does it do?
It takes the power harvested from the trimodal system to run itself, and its primary job is
Turns it into ones and lees.
Exactly. It translates it into discrete digital spikes, the ones and leers that an external computer can actually understand and compute.
But the data is still trapped inside the skull. How do we safely get those ones and ears out into the world?
Through layer 5, which is the wireless near-field communication, or NFC layer. This is a gigahertz frequency antenna built into the outer edge of the scaffold.
Like tapping my credit card at the grocery store.
It operates on the exact same basic principle. It bounces all that highly encoded digital data safely out through the physical bone of the skull using near-field magnetic induction.
Which is crucial because it means there are no physical wires piercing the skin of the scalp. The skull remains completely sealed, meaning there is practically zero risk of long-term infection, which is a huge hazard with current deep brain implants.
Exactly. The signal is received by a small wearable receiver, perhaps built into a pair of glasses or a headband worn by the user.
And finally, that brings us to the top of the stack, layer 6.
Layer 6 is the external AI decoding and neurofeedback layer. This is the heavy lifting. It's the external wearable computing unit.
Like the processing hub.
Right. It utilizes advanced transformer-based deep learning models to make sense of the massive multimodal quantum resolved data stream it's receiving.
So it's looking for patterns.
Yes, it looks for the patterns linking the quantum effort data, the biophotons, and the mechanical shockwaves, and decodes what the brain is actually trying to say. If we connect this to the bigger picture,
Yeah.
looking at these 6 layers, this isn't just one sensor. It is an absolute symphony of biological, chemical, mechanical, and quantum components.
And the most beautiful part is that it is designed to operate in perfect, silent unison without ever piercing a single brain cell.
It is a holistic reimagining of how machine interfaces with biology.
Which naturally leads us to Section 8, what this enables, the radical future. Let's
Yeah.
say we pull this off. We successfully synthesize the yeast, build the stack, and install this 6-layer device on a human brain. What does this radical future actually look like? What can this do that a Neuralink cannot?
It completely rewrites the ceiling of what a brain-computer interface is capable of. As we discussed, current BCIs read motor intent.
Moving a cursor, playing a video game.
Right. But because this device accesses the prefrontal cortex at the fundamental quantum optical level, it possesses what Enfield defines as semantic resolution.
Semantic resolution, meaning it can understand meaning, not just movement.
Exactly. It can distinguish between different states of working memory. It can read an imagined word, comprehend a spatial relationship, or decode a highly complex abstract concept like the feeling of nostalgia or the logical structure of a math equation before you ever make the conscious decision to speak it aloud or write it down.
Wow.
You are decoding the thought itself at its genesis, not the physiological shadow of the thought.
And that leads directly into the therapeutic speculation of the paper, which frankly might be the most globally important part of all of this. We aren't just talking about controlling an iPad with our minds. We're talking about closed-loop neurostimulation for mental health.
Yes, this is where the medical implications become staggering. Conditions like major depressive disorder, severe PTSD, obsessive-compulsive disorder, and schizophrenia are increasingly understood by modern psychiatry to involve severe dysregulation of prefrontal circuit dynamics.
The networks get stuck.
Yes, they get stuck in what are called pathological attractor states. It's like a record skipping, playing the same agonizing loop of anxiety or depression over and over.
And how do we currently treat those skipping records?
With pharmaceuticals, which flood the entire brain with chemicals, or with hardware treatments like deep brain stimulation or transcranial magnetic stimulation.
But those current hardware therapies are incredibly broad.
Very broad. They blast whole regions of the brain with continuous electricity or strong magnetic pulses, hoping to shake the record player until needle jumps out of the groove. It's highly imprecise.
It's like using a massive sledgehammer to try and fix the tiny, delicate gears of a Swiss watch. You might stop the record from skipping, but you cause a lot of collateral disruption.
Precisely. Or rather, to draw the distinction, current therapies are blind. They stimulate constantly whether the patient is actively having a depressive episode or not.
But this device is different.
Completely different. This ambient quantum interface operates at the resolution of a single dendritic branch. Because of that semantic resolution, it can detect a pathological attractor state forming in real time.
So it sees the spiral starting.
It can see the exact millisecond a depressive spiral or an obsessive thought pattern begins to crystallize in the working memory.
And because we established back in Section 5 that the Fee-Fi-Re interface is bidirectional, a two-way street,
Yeah.
it doesn't just watch the thought happen.
No. It can immediately intervene. The moment it detects the pathological quantum signature, the AI in layer 6 calculates the precise counter frequency.
And sends it back.
Exactly. The implant then sends a precision-targeted microscopic quantum optical perturbation back into the neural circuit to disrupt the attractor state and correct the network in real time before the patient even consciously registers the negative thought.
So what does this all mean for the future of medicine? It means that severe cognitive illness could become something we can continuously, silently debug at the hardware level. We aren't just giving people chemical coping mechanisms. We are fundamentally correcting the dysregulated quantum code of the brain as it happens.
It provides the physical, architectural basis for a genuine, high-fidelity cognitive neuroprosthetic.
But I know what you, the listener, are probably thinking right now. You are listening to us talk about quantum yeast wires and telepathic AI therapy, and you're thinking, well, this all sounds amazing. It sounds like a beautiful utopia, but it also sounds like the plot of a sci-fi novel. Is any of this actually real, or is this just a thought experiment?
And Enfield anticipates that exact skepticism. He addresses it directly in Section 9 with his integration agenda.
Yes, Enfield explicitly states that this paper is a forward research agenda. This device does not currently sit on a lab bench anywhere in the world.
Right, it's theoretical.
But He makes a compelling argument that he isn't making up new physics. He isn't relying on magical future materials. He outlines a highly specific, logical, six-priority roadmap to physically build and prove this device using tools that exist today.
Yes, he does.
Let's walk through that integration agenda logically because it shows exactly how a scientist attacks a problem this big. Where is the absolute first place you have to start?
You have to start by proving the biology works. Step 1 is to synthesize the SUP35 yeast prion in a lab, incorporate the specific aromatic tryptophan insertions we discussed, and then use cryo-electron microscopy to visually confirm that it actually folds into the correct parallel pi-stacked structure.
You have to prove you can physically build the spiral staircase.
Exactly.
Okay, so you build the protein wire.
Yeah.
But just because it looks like a wire doesn't mean it acts like one.
Right. So step 2 is proving it holds a quantum state. Enfield proposes using a technique called 2D electronic spectroscopy.
What is that?
This is a highly advanced laser technique that essentially takes a femtosecond speed movie of the electrons. The goal here is to check the coherence lifetime. They need to prove that the synthetic organic wire actually holds a quantum superposition state at room temperature, surrounded by thermal noise, without the state collapsing.
Okay, so you have a wire, and you prove it can hold quantum data. What's the next logical hurdle?
Proving it can jump the gap. Step 3 is to test the FRET coupling. They need to take the synthetic yeast scaffold, place it next to isolated brain microtubules in a petri dish, and prove that the energy naturally and efficiently transfers across the 2 to 5 nanometer empty space without the materials ever touching.
Right, proving the tuning forks actually sing together. Then, once you know the data crosses the gap, you have to prove your sensors can read it.
Which brings us to step 4, validating the nanodiamond NV centers. They must place the biomineralization layer on top of the active scaffold and prove that the diamond defects can accurately and reliably read the incredibly faint magnetic spin states of the aromatic network underneath them.
And obviously, all of this requires power.
So step 5 focuses on the trimodal energy harvesting. They would build a synthetic tissue phantom.
That's a tissue phantom.
Basically a physical mock-up of the brain's environment that mimics the physical heartbeat jiggling, the 37-degree heat, and the radiation profile. They need to test the implant in this phantom to ensure the beta-voltaic, piezoelectric, and thermoelectric systems actually generate enough aggregate continuous power to run the microchip.
And finally, if you pass all 5 of those bench tests, you arrive at step 6.
In vivo animal testing. You surgically place the full scaffold on the pile surface of the cortex of a living animal model. Crucially, you would simultaneously record the animal's internal brain activity using traditional deep brain electrodes.
To compare the data.
Exactly. By comparing the classic electrical data from the deep tissue with the ambient quantum data collected by the surface scaffold, you prove once and for all that the scaffold is accurately reading the precise cognitive state of the living brain.
And the crucial takeaway here, the reason this paper is so important, is that none of these individual steps require impossible leaps in physics.
No, they don't. The foundational pieces are already scattered across the scientific community. The quantum biology of microtubules is actively being studied by major research teams in Tsukuba, Japan, and at the University of Arizona.
So people are already looking at this.
Yes. Engineering amyloid scaffolding is an established subfield of biochemistry. Nanodiamond NV centers are already being heavily utilized in commercial quantum sensing.
Enfield is just the first person to stand back, look at all these completely disparate fields of science, and realize they are all puzzle pieces that fit perfectly together to solve the BCi rejection problem. The ambition of this paper is integration, not invention.
He is providing the blueprint for others to follow.
And that brings us to the end of our deep dive. The core takeaway for you today as you go back to your life is this. The era of the metal electrode, the era of the splinter in the brain, is coming to an end. The future of the brain-computer interface isn't going to look like a rigid microchip, and it isn't going to require massive brain surgery to install.
It's going to be organic.
It is going to be an organic, invisible, quantum optical conversation, using the very building blocks of life to finally speak the brain's native language.
It represents a profound philosophical shift in engineering. We are moving away from forcing the complex human brain to adapt to our primitive silicon technology and moving toward adapting our technology to the absolute, fundamental quantum reality of the biological brain.
And I want to leave you with a final provocative thought to mull over, something to explore on your own that builds on all this, but takes it one step further. We spent an hour talking about how a simple engineered yeast protein, something totally foreign to the mammalian body, can act as a perfect frictionless translator between human consciousness and a computer, utilizing the laws of quantum physics.
Correct.
If that is true, what does that say about the universe itself? Could it be that all biological matter, from the simplest fungal yeast cell to the highest order human neurons, is inherently, fundamentally wired from the beginning of time to communicate across these invisible quantum channels? Perhaps the universe isn't a collection of isolated biological islands. Perhaps it is one giant vibrating quantum network, and we are only just now finally learning how to build the microphone to hear the language.
It's a question that completely redefines everything we thought we knew about the nature of life.
Think on that the next time you look at a plant, or marvel at your own thoughts. We'll catch you on the next deep dive.